In the previous video, we looked at degrees of freedom just in terms of calculating them. Here we're going to look a bit more at material balances. And so we know that our number of degrees of freedom in our system is equal to our number of unknowns minus our number of independent equations. We talked a little bit about the different ways you can find those independent equations. And then we looked at a specific example for olives being extracted to oil and solids only. And so if we return back to this example, in this form here, the way it's written out now, there's no way to solve the system for mass flows. We need an extra piece of information. And so if we give that extra piece of information as the solid weight of the weight of solids in stream 1 is 0.9. We had said when we had done our degrees of freedom that there was essentially 3 independent equations that we could use. 2 of these were material balances, and these were for oil and solids. And then one of these was a physical constraint. And that was that our weight fractions in stream 1 of oil and of solids, when we add them together, they're going to be equal to 1, right? So we can use this physical constraint right now, and we can solve that this is 1 minus 0.9. This is equal to 0.1 if we had that other piece of information. And so now here, I can use my 2 material balances to solve. So these 2 material balances are the 2 independent ones, but there is a third one as well. And we generally see this with these types of systems, any system that's non-reactive for the start of this course. And so what we had said was that generally material balances, we have a number that are independent, one for each molecular species. And so in this case we have 2 molecular species, oil and solids. And so our balance on oil is the flow in stream 1 times the weight 1 of oil, the weight fraction of oil, being equal to M2, and that's oil only in that stream. Now I could also write W2 oil plus M3 W3 oil, but here this term is going to be 0, and so that's going to take out that second part of the equation, and then this term is going to be 1, and so it's going to go away because that stream 2 is pure oil. I can do the same for solids. So here M1 W1 solids equal to M3, right? Again, I don't have to write out those other 2, although I could write out those other parts of the equation and then take them out. I also have a third balance, which is the overall balance. And this is M1 being equal to M2 plus M3, just a total mass balance, everything that's going in equaling to everything that's going out. So I have 3 balances, but only 2 of them are independent, and that's because I can find the third one using the other 2, using a combination of the other 2. And so we can prove this mathematically, but generally in this course we're going to say that our number of independent mass balances is equal to the number of chemical species, or molecular species as we saw above. So here with this problem, given this information, I could use my balance on oil to solve or my balance on solids to solve. And if we use those balances on oil or solids, we can figure out M2 or M3, right, those mass flows. Once we've figured out either M2 or M3, we could also use the overall balance to solve, right? So in this equation, the overall balance equation, we have two unknowns, where the other two, we have one. So the question is, why can't we use all three of these balances to solve this system when I have more unknowns? And the answer to that we can test out if we just take away that 0.9 there, right? So here in the system now, we would have some more unknowns. These two weight fractions would not be known. And then we still have this physical constraint equation here. Now if we try substituting all these equations into one another, we're going to find that we don't have enough independent equations to solve this entire problem, but we can try. So here in these equations, all of them have two unknowns, right? So let's say I'm going to number these equations 1, 2, 3, and 4. So if I sub number 2 into 2 and 3 into 4, what I'll get is that M1 is equal to M1 times W1 oil plus M1 W1 solids, right? So M3 is equal to M1 W1 solids, and M2 is equal to M1 W1 oil. And so here in this equation, I still have two unknowns, so I'm going to sub in M1 equals M1 times W1 oil plus W1 solids, and so these are going to be equal to 1, and then in the end I get M1 is equal to M1, right? Which doesn't actually tell me anything useful about my system. And this is the sort of idea with independence of equations, is that if I can combine any two of these equations to get the third, then they're not independent of each other. So we're going to assume that the number of independent mass balances is going to be equal to the number of chemical species. There are a few exceptions to this, but these are, we're going to see how we can spot those. For now, in these cases, we see that when we sub in two of these equations or add them together, we get this third equation. So for example, if I said 2 plus 3, if I add those two equations together, I get M1 W1 solids plus M1 W1 oil. So those I take from this side over here, equaling to M2 plus M3. And then this I know will reduce down to M1, equaling to M2 plus M3. So by a linear combination, a combination of these two, I can get this equation number 4. And so equation number 4 is not giving me any new information on the problem than equation 2 or 3. So I'd encourage you, you can try to solve this problem right here with these 4 unknowns using these 4 equations. You won't be able to do it until you get an extra piece of information like that W1 solid is equal to 0.9. And so for our purposes, we're going to take that our number of material balances for these systems that are non-reactive is going to be equal to our number of components. So in this case, 2 oil and solids. Those are our independent material balances.